Hey there, and welcome back. Today we're going to be talking about momentum. And momentum is one of the most interesting phenomena in the universe. This is something that took people a long time to work out. Again, it was the brilliance of Newton who put it together based on Galileo's ideas. We've already gone over the three laws, but you're going to see that momentum is necessary in those three laws. Just as inertia was necessary to explain the first law, momentum is necessary to explain the second and even the third laws. Actually, all of them, if you really want to get into detail on it. So we're going to be talking about momentum. We're also going to be talking about something called impulse as well, right? When you basically a hit or a strike onto something, and the force that is exerted when that happens. So what is this momentum? Well, momentum explains a couple of phenomena, and some of these are really serious phenomena, like how to make rockets move through space, how to build safer highways, things like that. But sometimes you just get really slapsticky, funny things, and I thought that I would go ahead and put a couple of pretty funny little clips in this presentation just because physics tends to be a fairly serious subject and it's fun to laugh sometimes. And I'm going to start by this guy here. This is a bowling tournament. We're going to see momentum in action. Here he's in front of this whole audience. He's sponsored by Denny's, by Geico Insurance, so you can tell this is on TV. And watch what happens here. It's so funny. Actually, I'm gonna watch it again. I mean, you feel bad for the poor guy, but he should have taken this physics class and know something about momentum and when to let go of that ball. I'm sure he didn't intend to hold on to it that long, but that's a pretty funny video. Um, anyway, it also explains something that we've all known for a long time. It's this thing called Newton's cradle. Actually, Newton didn't invent it, but it's this thing right here. Right? Why is it when I pull back on that ball right there that it swings over it, but the other two don't move? Okay, this is actually a demonstration, as we'll find out, of the laws of conservation of momentum. Really interesting, and of course they put it over a copy of the Principia of Sir Isaac Newton, which is that famous work that he did that laid out the three laws. So what is momentum? Well, momentum is it's kind of like inertia, except we're able to actually put numbers to it. Remember, inertia was something we used as a descriptor of things, right? That things had a certain inertia to them, that they tended to not be moved very easily or to change direction very easily. Momentum is a more specific way of putting it. So momentum, it turns out, is a property of moving things. Now, we've already learned that essentially all things are moving. It just depends on what reference frame you're looking at, right? So even if I just take this pen down, I put it on the table, we could say it's not moving, but it's moving relative to a rotating Earth, and it's moving not only relative to a rotating Earth, but to a orbiting Earth around a very large sun that is then in turn orbiting. You get the idea, right? So it depends on the reference frame. Um, Basically, momentum means inertia in motion. Um, More specifically, mass of an object multiplied by its velocity. So this is the first time we're able to take two numbers, put them together, and say that is momentum. That's a tendency for something to happen, a property of moving things. And so in equation form, we usually write it as P equals mv. And remember, v is a vector here, and in this case, momentum is also a vector. Mass is a scalar, so that hasn't changed. And so you can imagine the momentum of this elephant, if it's charging at us, which is in fact it is doing in this picture, it's going to have tremendous momentum because it's a big animal and it's coming at us pretty quick. Trust me, elephants can be pretty fast. All right. So another example of momentum would be, this large boulder right here, right? This boulder is actually kind of at rest, where it has a velocity of 0. So we would say that it has no momentum in this reference frame. This is what this says here. A boulder at rest has no momentum. But what if this person was Supergirl, Superwoman, right? And she was able to push this thing down the hill. What would happen? Well, a moving boulder has more momentum than a stone rolling at the same speed. And in this context, the word stone here means a smaller rock, right? So a stone would be something maybe about as big as her foot or something like this. So all things being equal, if they're both going at the same speed, this is going to have much more momentum because it's very large. A fast boulder has more momentum than a slow boulder. It's another thing that's pretty obvious, right? The faster it goes, the more momentum it's going to have. Mass times velocity. Very straightforward. So it starts to get a little complicated when we start thinking about this concept called impulse. All right, we're going to be coming back to momentum here in a couple of slides, but we need to understand what impulse is. And impulse is the product of force and time. So force times time. In equation form, it's Ft. Well, J is the symbol we use for impulse, so it'd be J equals Ft. So you'll see J used several times in the next couple of lectures. So what would be an example of an impulse then? Well, a brief force, remember brief meaning brief in time, a brief force applied over a short time interval produces a smaller change in momentum than the same force applied over a longer time interval, right? Because it's force times time. In other words, if you continue to apply the same force and you just increase the time, the impulse gets larger. That's all it's saying. But you can also fix it the other way, right? If you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. Oh, this is an interesting thing here. Change in momentum. Remember, momentum is mass times velocity, right? So really an impulse is starting to look like it has something to do with a change in momentum, okay? So impulses change momentum. Let's look at this. The greater the impulse exerting on something, the greater the change in its momentum. Makes sense, right? You put something on there, you apply a force, especially a heavy force, over a very short period of time, you're going to get a very rapid change in momentum. Impulse and momentum have the same units. This is really interesting, actually. Right? Force times time and momentum, which is mass times velocity, have the exact same units, which is to say the Newton second. So usually written as an NS. And in the equation form, we can demonstrate this relationship in this way here, that J equals the change in momentum. Or force times time equals the change in mv. And remember, this change is applied to both the mass and the velocity. This is something that is kind of important. We're going to come to, especially towards the end of class when we talk about Einstein. We're going to make some assumptions about this as we go forward. Basically the same assumptions that Newton wound up doing. And so here we can see, again, in lecture 5, when I was talking about Newton's third law, I showed a woman pushing a car. Here's another woman pushing another car. Again, the guy is in here. And she's applying an impulse on the car to her not very helpful husband, boyfriend, or whatever he is, brother, whatever he happens to be. So let's look at this case here. That impulse changes momentum, right? Let's go through the reasoning on this. So let's show how impulse increases momentum. So you apply the greatest force for as long as possible and you extend the time of contact. In other words, you put in a very heavy force and instead of hitting it just for a real short little quick nick, you give something a real good long exposure to that force. Now, force can vary throughout the duration of contact. So just because you originally put force on it doesn't mean you're putting equal force the entire time. You really are going to be looking at an average force over the time of that contact. So for example, when a golfer swings a club, so here's the golf club hitting the ball. So you can see this is actually right in the process of hitting it right as this photograph is taken. And the ball and the club have actually been in contact this entire time, right? So the moment that the ball hits the club, there's actually a period of time they stay in contact. And the longer they stay in contact, the greater the impulse and the further you can drive the ball. So a golfer swings a club and follows through. The same thing is true for a baseball player who hits a ball and follows through. In other words, when they swing through, they make sure that they're basically swinging the club towards the ball so that they stay in contact for the maximum amount of time. The great power hitters of Major League Baseball, for example, have these very long swings. It causes them to strike out a lot. But the payoff for them is that they keep their bat in contact with the ball when they do in fact hit it that much longer, and that allows them to hit them further and get more home runs and doubles and things like this. If you're not familiar with Major League Baseball, well, look it up on Wikipedia. All right, so we just showed an example from sports, how impulse changes momentum. Let's use another example here. Let's use, in this case, I'm going to use a locomotive, right? So case 2, it would be decreasing momentum over a long time, right? You don't necessarily want momentum to change. Remember, an increase or decrease is the same thing as a change. So a change in momentum requires an impulse. So even decreasing momentum requires an impulse. So for the case of stopping a train, that impulse is hitting the brakes. Now you don't want to hit the brakes too fast because you're going to have a major change in the momentum, and that is not the way you want to do it. What you want to do is you want to hit the steam brake and have it slowly bring you to a stop, right? Which has the positive effect of extending the time during which momentum is reduced. Why is that important? Because it means that you can sit on the train, don't have to worry about being thrown on the floor. So here's another case that we need to kind of keep in mind is when a car is out of control, it is better to hit a haystack than a concrete wall. That's so obvious. Why? Because as you're hitting a haystack, you actually take some time to slow down, right? All that deceleration, all that slowing down, all that change in velocity, right? That impulse is exerted over a much longer period of time than if you hit a wall. If you hit a wall, the force is still the same. It's just that the time, is very, very short. So you get a massive impulse, right? So physics reasons, same impulse either way, right? You're getting a massive impulse, but extension of hitting time reduces the force, right? So impulse is J equals force times time. So here's a guy, I found him when I was doing this slideshow, and he basically has a swimming pool in his backyard. The top part of it is frozen, and he's intending to break through. And the reason why he's intending to break through is because he thinks that it would be fun to get it on video. It's kind of like this, like an ice bucket challenge or something like that. Anyway, you can see that he makes a serious miscalculation. And you tell me which kind is he hitting the concrete wall or the haystack? It turns out he was totally fine, but it's funny. Let's watch it again. All right, so you can see he jumped in, and actually right before he did the jumping in, he had all this obnoxious things to say, and I believe that the video is also on YouTube, so you can look for it there. But anyways, yeah, he wound up basically not hitting the haystack, which is to say going into the water and slowing the period of time over which the impulse is exacted on him. Instead, he hits the ice. And the result is that it's like hitting a concrete wall, right? All that impulse hits right at one time. Here's another example, right? So in jumping, bend your knees when your feet make contact with the ground, because the extension of time during your momentum decrease reduces the force on you. All right. So it basically says is you bend your knees, and what that does is it allows that change in momentum to occur over a longer period of time. And in doing so, it doesn't hurt as much to jump onto things. Of course, there's limits to how high you can jump. So in boxing, you would ride with a punch, okay? And so, again, another image. This video should be titled Karma. Again, dealing with the question of who wound up getting the brick wall and who got the haystack. So you be the judge. Yeah. So yeah, she pushes him in the water and he's completely fine, and then she eats it on the concrete, right? So, anyways, another case, right? Decreasing momentum over a short time. So, a short time interval produces a very large force. So, for example, a karate expert splits a stack of bricks by bringing her arm and hand swiftly against the bricks, right? We've all seen it, where they break bricks or they break ice sheets or whatever it is that they're breaking at that time. Um, Against bricks with considerable momentum. That's the point, is they want to get large amounts of momentum. So if they don't have large arms, they better be moving very fast to get the momentum up. Time of contact is brief, right? To be able to exact the largest force when they're doing impulse, right? And force of impact is huge. So here's a case where this guy is going to jump over these two. He's a karate expert. I believe he's probably Russian because this looks like the Cyrillic language written back here. Anyways, his target is this, and unfortunately, this made the internet not because he's such a good kicker, it's because he misses the target. Well, you'll see what he does. Yeah, so that didn't work out too well for the target, right? Poor guy got it right in the face. Let's watch it again. So it's just a good thing he turns out that he's okay. All right. There's some really interesting stuff that comes out of momentum and impulse, right? So using impulse and momentum to derive Newton's second law, which is cool stuff. This is actually what Newton did to derive the second law, F equals ma. He didn't actually derive it in the way that the textbook I typically use shows. He actually derived it uh, from an argument for momentum, using the math of momentum, that mass times velocity equals momentum. And also noting that the force, or the sum of all the forces times time, which this is just a fancy way of saying impulse, force times time, uh, equals the change in momentum. That's what we've been writing since, well, back here, right? It's just a fancier way of writing it this way, right? That's what this is. Gotta go back through. All right. So basically, you just take this equation right up here up on top, divide both sides by delta t, or time, right? You're just dividing it by time. And so it turns out that force is just equal to the change in momentum over time. That's all it is. So force is basically the definition. The definition of force, as Newton originally saw it, is the change in momentum, and that's very cool, right? Because this ties into what Galileo was saying, was that inertia, that things don't want to move. Newton's first law came about, and he said you have to have an unbalanced force to move things that are in motion or at rest. This is really just a statement of that, right? Delta P, which is, say, the change in momentum with respect to time over the change in time, right? Usually that's just T, because we usually do it's T2 minus T1, but T1 is usually equal to 0 just because it's convenient to do that. So it's usually just T, so don't get freaked out by this. And we just have to remember that momentum is equal to mass times velocity. So we could just take that P and swap in an mv for it. That's exactly what Newton did. There should be parentheses around the mv. Unfortunately, I didn't put them in here. But anyways, there should be a delta parentheses mv, and the v is a vector, the force is a vector. Of course, time and mass are not. All right, so the next thing that we do is we make an assumption. We should have written this assumption out, is that it's the change in the mass and the change in the velocity. Well, can you really have a change in mass? Well, this is a complicated topic, and by the end of the class, you'll realize that yes, you can have a change in mass. But when Newton put it together, he said, no, you can't have a change in mass. It wasn't until Einstein came along that we realized that that can happen. So, but for everyday use, for even interplanetary movement, it's fine. We're just going to go ahead and make the assumption that mass is always mass. And so if that's the case, we can just take that right out. There's no such thing as a change in mass. So we just take that right out and we multiply it right up front. and basically treat it like it's a constant. Right? It doesn't move. It doesn't change. However, that leaves us with the change in velocity over the change in time, and that's pretty cool because we just need to remember that the change in velocity over the change in time is just acceleration. So then we plug in the a right here and we get F equals ma. So in fact, Newton derived his second law as the change in momentum. That was originally what he wrote and worked through. But when we make the simple assumption that mass doesn't change, all of a sudden F equals ma works right out. But you need to realize that change in momentum is the same thing as a change in change in momentum is force. So we're going to start getting into some new laws. And this is going to be, other than Newton's first three laws, we now have a new one, right? The law of conservation of momentum. So basically what it says is, in the absence of an external force, the momentum of a system, and I cut off the bottom of the y, it's there. So a system remains unchanged. So P initial, this is basically the math of it. It's very straightforward. It just means that the P initial, which is momentum, the initial momentum in a system, is equal to the momentum at the final. You can't lose it, right? What happens at the beginning has to be there at the end, right? And if you can't find it, you got to look for it. It's there. So where I is the initial, F is final. So beginning and the end have to be equal. It can also be written as mass times velocity initial, mass times velocity final. This is a really important, this is actually a relationship I would probably write in my notes. Okay, so we're going to be getting into why this is important. This person here obviously did not study conservation of momentum, didn't study anything about energy, which will be in a future chapter, and you're going to see the mistake she's about to make, which is she's on top of this, I guess it's a medicine ball, and she's in her apartment standing on top of it for whatever reason, who knows, but she's about to pay for it. Yeah, that's not a good way to go. Yeah, just twice. I gotta watch it twice to really let it sink in. Anyway, it turns out everybody's fine. She did put a dent in the wall though. Anyway, so this is what we would call an elastic transfer of momentum, also known as a collision. Okay, we're going to be talking about this. So conservation of momentum. Examples: when a cannon is fired, the force of the cannonball inside the cannon barrel is equal and opposite to the force of the cannonball on the cannon. Right? That's Newton's third law. The cannonball gains momentum while the cannon gains an equal amount of momentum in the opposite direction, which is to say the cannon recoils. In other words, it pushes back. And here's an example of this. Here's an artillery piece. They're going to fire it. And so if it's going to fire a projectile actually away from you into the screen, or away from you towards the screen, it implies that the gun is going to move back towards us. And let's see if that actually happens. That's the prediction that Newton would make. Yeah, you can see that that in fact did happen. Okay, let's try it again. Yeah, so it kicks back, right? So another important part to keep in mind is when no external force is present, no external impulse is present, and no change in momentum is possible. So it's important to have an external force in order to get a change in momentum. If you're dealing with a closed system, like remember in lecture 5, we're talking about Newton's third law. We showed that the orange was sitting on her cart and the apple was pulling her along. And as long as they weren't part of the same system, he can always exert force on the floor through friction and pull her in her cart. But if she was just sitting there in her cart, she can't just sit there and move back and forth or try to nudge it inside and expect the cart to just go on its own, because she's part of that system. It's the same reason that when you're in your car, you can't get your car to do strange stuff just by moving around inside of it, right? You notice that a housefly moves at the same speed inside of your car as it does inside your house because everything is relative. It's all part of your system. It's not suddenly stuck to the window at the back of the window just because it's inside the car. Neither are you. This is the same concept. So this gives rise to a really cool conversation that we should have about collisions. And there are two kinds of collisions. There are elastic collisions and there are inelastic collisions. So basically, an elastic collision occurs when colliding objects rebound without lasting deformation or any generation of heat. In other words, they hit and they bounce like two rubber balls. So these are actually graphics. So this is where you have masses that are equal that hit each other. Let's see what happens. This one's got momentum at some velocity. It's going to move this way towards m here. Remember m and m, so they're of equal mass. Let's see what happens. Pretty straightforward stuff, right? It transfers the momentum. It doesn't lose the momentum. The momentum is transferred. Okay? So hopefully you remember this part, right? This is basically what that chart is explaining is the principle of conservation of momentum. This ball over here has momentum and it transfers it through these three balls to this other ball, which then moves up through an interesting argument regarding energy and then back. We'll get into the energy argument in the next lecture. So what about if the masses are unequal? Does something strange happen? Yeah, something a little strange, but it turns out that the math that you will be learning in future chapters will explain it. So that's where masses are equal. This is masses are unequal. Now notice the impact, and this one actually starts to move backwards and this one goes forwards. Let's do that again. That's an interesting one to see. Notice how this one moves away at a much greater speed than it had previously. I'm going to do it one more time just to really let it sink in. Much greater speed moving away. Okay? So the different bounce that exists here on where the masses are unequal is because of a difference in something called kinetic energy. But we'll leave that till the next lecture. So in contrast with elastic collisions, where they bounce, there's no deformation, which is to say, like if a car hit another car, these cars wouldn't even leave a dent, right? They just bounce right off like they're rubber. But of course, cars aren't made that way. They actually behave in an inelastic way. So an inelastic collision occurs when colliding objects result in deformation and or the generation of heat. In other words, energy would be lost in this way. So a perfectly perfectly inelastic collision would be where you had one thing run into another thing and then they stuck together permanently from that point forward. So this would be a good demonstrator for that. These have equal masses, and we'll see what they do. This one comes forward, they fuse, and look, the velocity at which it's moving is half the velocity. Because momentum is conserved, right? If this one came in at speed mv, but this one is coming in at basically with no momentum of its own, it's going to move at the average of the speed of the two. That's common sense, actually. Cool stuff. All right, but these things are where they're just in a nice linear straight line. But most objects don't hit that way. Some of them do, but most don't. So what happens when they hit like at a glancing blow? You know, they hit off of the edge of something that's round or whatever. So in this case, you create a parallelogram of the vectors describing each initial momentum to find the combined momentum. We actually did this in when we're talking about Newton's third law, where we actually resolve vectors. And I drew a similar parallelogram, and the textbook I like to use also has how to draw these parallelograms in there. But here's an example of a coin that collides with another coin after being slid across the table. So these are Swiss francs that are being slid across the table, and let's see this animation here. So you see that they're drawing the directions, and the arrows represent the magnitude, right? The magnitude of the vector. Let's watch that again. So let's watch that again. So it turns out that some simple geometry allows us to resolve these things using simple vector designs, right? Another example would be a firecracker exploding. So in this case, we have a firecracker that's falling, and this is out of my favorite textbook here. It falls and then it breaks, and as it explodes, I'm sorry. And as it explodes, it ruptures half of it in one direction, half of it in another direction. So we know that the mass times velocity, the momentum, has got to be conserved, right? That's the law of conservation of momentum. So what happens? So a firecracker exploding, the total momentum of the pieces, notice this says pieces, not the total momentum of this part, after the explosion can be added vectorially to get the initial momentum of the firecracker before it exploded. That is neat. Look at this. Here we've got the vector of the very first chunk here. It's right here. So here's its vector, and here's the vector of this one over here. And it turns out that if you do vector addition, which you're basically learning to do using these parallelograms, but when you do the vector diagram, you find out that mv, the initial momentum, is the same as the falling object. And we'll come to a realization as to why that is in a couple of lectures ahead of us. But fascinating, right? You're dropping something, it explodes, and the momentum calculation still moves as though it was still intact. Fascinating. All right, so let's do a practice problem, just so that we can make sure we've got this down. And the best way to do this is, I thought, was to look at a couple of pirate ships. So here's a couple of pirate ships, Ship A and Ship B. And they're on the high seas, and these two pirate ships have decided, they decided to do battle. Ship A, these guys over here, is armed with 12-pound cannons that fire, you guessed it, 12-pound, which is a 5.5 kilogram cannonballs that fly at 300 meters per second. That's just under the speed of sound. Sound is about 340 meters per second. Ship B is armed with 18-pound guns, which are 8.2 kilograms, that has cannonballs that fly at 250 meters per second. All right, so they've decided to do battle. They've got these guns. One's a 12-pound gun, the other one's an 18-pound gun, and the cannonballs fly at slightly different velocities. So during the battle, two guns aimed directly at each other fire, and their cannonballs hit in midair. The collision causes the balls to fuse. In other words, they fired at each other, the balls hit in midair, and they fused. So the collision causes the balls to fuse in a single hunk of metal. Which ship, if either, does the fused cannonball hit, and at what speed? Wow. Can we solve that? Of course we can. We just use conservation of momentum. It's a very, very straightforward calculation. So here we have Ship A firing its 12-pound gun. These guys are firing their 18-pound guns. The cannonballs hit in midair. Where's the ball go? Does it go and still hit Ship A? Does it hit Ship B? And if it hits Ship B, does it do any damage to it? What's the velocity at which it hits it? Let's look at it, okay? So we're going to do this using our chalkboard. All right, so this should be fun. We're going to see who's going to get hit by the flying hunk of metal that's created by these two cannons shooting at each other at exactly the same time. So Ship A fires let's just go ahead and put the data right here, 12-pound. Remember, 12 pounds is 5.5 kilograms, and it fires it at 300 meters per second. Ship B fires a much heavier round, 18-pounder, which is 8.2 kilograms at 250 meters per second. All right, so in order to do this, it's just straightforward conservation of momentum. All right, so that's just going to be this, right? P initial equals P final. Sorry, I do kind of a fancy little F for my final. And we have to ask ourselves, what is the P initial? Well, all we need to do is take the momentum of the original condition. So ship A is firing 5.5 kilograms at a velocity of 300 meters per second. All right. We need to add that to this group over here at 8.2 kilogram for ship B times 250 meters per second. But we have to keep in mind something important here, that the velocity of ship B is negative. Why is it negative? Because the arrow is going the opposite direction. That's why I made sure that I pointed this out. Ship B is not firing in the same direction as ship A. Obviously, they're shooting towards each other. So we have a negative number here. So let's see what's going to happen here. So let's do the multiplication. So I went off screen really quick and pulled out my calculator. And so when I multiply 5.5 times 300, I get 1,650 kilogram meters per second plus a negative 2,050 kilogram meters per second. Okay, so these are actually Newton seconds, but we're just going to leave it as kilogram meters per second for right now. So which one is got the larger magnitude of momentum? Well, clearly ship B does, right? Because when we multiply these two, we get 1,650 kilogram meters per second, which is say 1,650 Newton seconds. Over here, ship B, that's what this is over here, their numbers, it's equal to negative 250 kilogram meters per second. All right, and so this equals some momentum value, right? So when we add these together, it has to equal P final. And so when we add them together, we get the following number, that P final is equal to negative 400 kilogram meters per second. All right, so basically what's happening here is the guns from ship B, even though they're firing at a slower velocity, that mass is so large that it's able to overcome and go to the left. In other words, the ball is going, the cannonball that is now fused is going to hit the ship that is located, it's going to hit ship A. All right, so we figured that out. But have we really figured everything out yet? No, it wanted to know what velocity is. So here we've got our velocity, or our total momentum. Our momentum says that ship A is going to be hit by this hunk of metal. All right, so let's erase our board. All right, so we know that P final equaled negative 400. So what does that mean? Well, we know that P final is going to be mass times velocity. The final velocity is going to equal negative 400 kilogram meters per second. All right, but we know something about the mass, right? The mass is just a hunk of metal that's fused. So we know that it's an 18-pounder plus a 12-pounder mixed together. And so we know that in kilograms, that would be 5.5 plus 8.2 kilograms times final velocity It's going to equal negative 400 kilograms meters squared. Cool. Let's do some arithmetic over here. We're going to have 13.7 kilograms times V final, negative 400 kilograms meters per second. All right, well, what do we do? It's pretty obvious. You divide 13.7 by both sides to isolate the variable. And so we're going to get a V final. I'm going to put it into my calculator. So that's a V final of 29 point, because kilograms cancel, they're on both sides, meters per second. All right. So what does that mean about our battleship, or our pirate ship battle here? These two things have fused. You have a hunk of metal that's flying at you at 29.2 meters per second. It weighs about 30 pounds. How much is 29.2 meters per second? Well, if you do the calculation kind of really quickly, and I've done it kind of on the, I just scratched it out really fast. It's a velocity of about 105 kilometers per hour, which is a little over 60 miles per hour. So it's coming fast enough to do some damage to a person standing on the deck, but almost certainly the armor or the wood of the side of the pirate ship for pirate ship A could probably take the hit. But granted, you wouldn't want to be hit by that. All right, so I hope that you kind of enjoyed that little exercise. It was a little longer than I thought it would be, but we went through some really cool stuff, conservation of momentum. Not only were we able to show that these two things would hit, but we showed which boat it would hit, and we showed at what velocity it hit, 29.2 meters per second, which is a little over 60 miles per hour. Cool. All right, so we just showed who won in that thing right here. That ship A would be the one losing, and that ship B would be the one winning here. All right, so there's some useful equations I wanted to conclude with. We got momentum equaling mass times velocity, impulse equaling force times time. Remember, J is this unusual symbol for impulse. J is also equal to the change in momentum, or we can also say this, that force times time, which is impulse, equals the change in mv. This is important for deriving Newton's second law, as we showed earlier. You don't actually, by the way, need to know how we derived it, but it is important to know that these things are interrelated very carefully. And those of you that go on to take a more advanced science class will be very grateful to know that relationship. Also keep in mind the law of conservation of momentum, that the initial momentum has to equal the final momentum, where I is final, F is final, where I is initial and F is final. It can also be written as mv initial equals mv final. We just did a pirate ship example here of two cannons firing at one another and who would win using that simple argument. So I know that there was a lot going on in this lecture, some of it pretty funny, some of it is kind of, might be a little intense at first. Give yourself some time to step into it, right? Don't do the homework last minute. That sort of thing is kind of the kiss of death, almost in any science class, let alone a physics class. So take your time, get to know this stuff, because in the end, you're going to walk out and you're going to say, man, I finally get what momentum and impulse and the relationship between Newton and sports, or whatever it is that my field is. You might start seeing that develop. All right, well, I hope you enjoyed it, and we will see you next time.